Okay, it's a real pleasure to have Stephen Wu here. He's going to be talking about his work on private machine learning, which is something that he has done a lot of great research in. So thank you, Stephen.
Thanks, Thomas. Yeah, thanks for having me. It's very exciting to be able to speak to you guys. So recently, I realized a lot of the work we've been doing in our group actually are very similar to a lot of great work coming out of Google. So as they usually mention, if you cannot beat them, you should join them. So hopefully this talk can open up many opportunities to talk and maybe collaborate. Hopefully some of the ideas can mix together, and we have even better ideas coming out of the conversations. So today in this talk, I will mostly talk about two pieces of work recently done with my collaborators. I would like to highlight the student collaborators in these two papers, Xiangyu Chen and Yinxue Zhou, who are excellent students at the University of Minnesota. And it's also joint work with my faculty colleagues, Mingyi Hong and Arindam Banerjee. So we're talking to folks at Google, feel like preaching to the choir about this point, but oftentimes when you train machine learning models on sensitive or private data, you might have concerns that these trained model might reveal lots of private and sensitive information about the training data. So there's a very nice attack, recent work led by Google researchers, including Nicholas Carlini, that basically show that you can actually reveal lots of interesting information by looking at some of the language model. So this talk is about the opposite, right? How do you actually take in sensitive training data and somehow output machine learning models with provable privacy guarantees? So the guarantee that we'll look at in this talk, and something that Google has invested a lot of amazing efforts in, is the idea of incorporating differential privacy in the machine learning model training process. Right? So I would really quickly go over the definition. I'm sure many of you have seen it many times, but the basic idea is to form a stability, right? If I change a person's data, say Alice data to Bob's data in the training data set, we would like to guarantee that the output distribution, say the distribution over the trained machine learning models, to be roughly the same. So if you see a machine learning model drawn from either of the output distribution, you can't tell whether Alice data or Bob's data was in the data set. So therefore, it can be providing some kind of provable privacy guarantee. So yeah, many of you have seen this definition before, but there's differential privacy is a formal and provide a quantifiable measure for this kind of stability guarantee. Usually, we call it algorithm epsilon delta differential private if it satisfies some stability guarantee in a probabilistic manner. Okay, so for the rest of this talk, if you haven't seen this definition before, don't worry about it. At least the intuition will be clear. So we'll focus one problem, and we just think about model training with differential privacy, and usually you can write down a simple formulation. Folks at Google have done it a lot, and potentially you guys do it better than anyone else. But in general, you can think about a simple formulation where you're taking n data points that are considered private, and you would like to train a machine learning model by minimize some loss objective. So here, we would like to minimize model denoted by X and the loss objective F, which is really just an average of loss function over the n data points. And we'd like to solve this problem subject to differential privacy. So this is a really well-studied problem without differential privacy constraint. And the sort of the go-to algorithm we think of is a differentially private variant of SGD. Right? So potentially you have seen some variation of this algorithm before, but basically you have this iterated algorithm like SGD, where every round you compute some kind of gradient estimate based on some randomly sampled mini batch. You add Gaussian noise or Laplace noise to the gradient estimate, and only use the noisy gradient estimate to update your model, and do it for some number of rounds. Right. So the way you think about the privacy guarantee of this algorithm typically is to prove that, first you have assumed that the loss function satisfies some property, like Lipschitzness. The reason you tend to assume this kind of Lipschitzness assumption in the proof is that when you make such assumption, you can guarantee that for any model at any point, the individual gradient given by any single example, the norm of the gradient is bounded by some constant L, right? So with that knowledge, you'll be able to set the variance of noise as proportional to this Lipschitz constant L, and you will actually, the intuition is that the noise will be able to hide the influence from any single example because the noise scale with the gradient norm, upper bound of the gradient norm. So therefore you can prove differential privacy. Okay, so this is what a theorist version of DP-SGD might look like, and you can prove theorems, guarantees about it. In practice, the actual algorithm you run actually look a little different, and this is largely due to a very nice paper from Google, actually, but led by Abadi et al. So here, you actually, oftentimes in many of the model training, even for simple models sometimes, you don't actually get to know the Lipschitz constant, right? So it's actually a constant that is very hard to obtain. For example, you might have to take worst case over all models or take worst case over all data points. So in particular, the way to guarantee this kind of low sensitivity or bounded influence from individual gradients is to perform a form of gradient clipping, right? So the idea is also simple. So whenever the gradient from any single individual example exceed an L2 norm by some threshold C, you just shrink the gradient so that the L2 norm is exactly C. If the gradient norms is already small and smaller than C, you don't do anything. So now you actually would take average over the clip gradients and use that as the gradient estimate on top of which you add Gaussian noise. Okay. So the privacy proof here is about the same. You just get to set the noise rate, the variance to be proportional to the clip norm threshold C. Okay, so maybe some of you have already seen it. I hope the idea is simple, even for those who haven't seen it. So at the end, you can prove some formal differential privacy guarantee by analyzing the noise rate and how it corresponds to the clipping threshold C. So this is not a surprising result. Basically, for those who work in this area, this is really thinking about a composition of a sequence of Gaussian mechanism because you're adding Gaussian noise to a sequence of statistics that correspond to gradient estimate. In composition, the entire trajectory actually satisfies the epsilon delta differential privacy guarantee. So you might wonder, what about convergence, right? So the clipping doesn't actually change the privacy proof much. It doesn't change the privacy guarantee much. Okay, so I want to use this as a starting point of this talk. And I would like to highlight that in the first part, we'll think about potentially the effect of clipping on the gradient estimate in this kind of gradient-based optimization problems. So the takeaway for you later will be that this sort of clipping effect can highly depend on what the gradient distribution or the geometric structure might look like. But later, I would like to actually take a slightly broader view and thinking about what clipping is really doing, right? Clipping is really just performing a form of projection on individual gradients. It's really a special case, right? So in particular, you can think about this kind of gradient clipping operation as really a L2 projection onto some ball, L2 ball radius C, right? And in principle, you can actually think about other forms of projection that might leverage more specialized structure of the gradients that may more tailor more to the geometric structure. So you can maybe think about projection of these gradients onto other type of sets that may not be an L2 ball of any radius. So that sort of leads to a second part of this talk. Hopefully I have enough time to get to it, where maybe you can think about some low dimensional structure of these gradients and think about how to incorporate projection in the training process as a form of dimension reduction to potentially achieve better accuracy. Okay, so this is sort of the roadmap for today's talk. So let me start with the first part in thinking about the clipping. So what would change if you actually do clipping when you optimize some objective? So let me give you a very simple toy example. So everything in 1D, it's really just estimating mean of a bunch of numbers. So I can write down a square loss objective across 3 data points, S1, S2, S3. So since this objective aim to recover the average of these 3 numbers, the optimum is actually x star equals 1. And you can think about how the clip gradient descent or clip differential private SGD operate on this kind of objective. So one thing you can do is that you can calculate the clip gradient at the optimal point x star, right, which is exactly the average one. And if you take average across all 3 points and you take expectation over all 3 points, the clip gradient at the optimal point x star, if you clip everything at the threshold 1, it's actually non-zero. So if you don't do any clipping, the gradient will be 0. But if you do clipping at 1, the expected gradient, clip gradient is actually 1/3. Okay, so it's a simple calculation. What that means is that if you actually run the clip gradient descent and you actually pass by the optimal point, clip gradient descent will actually push the iterate away from the optimal. Okay. Let me tell you another bad example. So it's a similar example about mean estimation. So I have another square loss objective where I want to estimate the mean of 2 points, 3 or -3. So the optimal is the average, which the x star is 0. So this has a different kind of bad phenomenon. So if you look at the clip gradient at any point within the bounded interval -2 to 2, that in particular contains the optimum 0. All of the clip gradient, expected clip gradient in this case, is actually flat, right? So all the clip gradient is actually 0. So what that means is that as soon as you start approaching to x star when you enter the interval -2 to 2, clip gradient descent basically lost all the momentum. Basically, it will not have, an expectation will not have any direction movement anyway, and particularly it would not point to x star. Okay. So you can run toy simulations with these kind of examples. Basically, no matter how many iterations you run, the iterate will stay far away from the optimum, the x star. So this potentially is not so surprising in light of some very nice results coming out from Google. I think this is a work by Sean Song, Thomas Donkey, and Pradeep Takata and Om Tucker, who basically showed that for a specialized cause problem, the GLM problem, which capture the problem in this case, the clip gradient descent method is actually optimizing a very different objective that you might perform some kind of hubridization on top of the objective. Okay. Okay, so this will, in the worst case, you can expect things like this could happen. Right? So there are lots of clipping bias, and doing this kind of clip gradient descent will basically take you away from the trajectory that converge to the optimal point. But you might be curious about what happened in many of the practical instances or many of the data set you might run experiments on. Yeah, is there a question?
Stephen, yeah. I had a question. Yeah. Hey. Yeah. So in like, if you deal with let's say high dimensional losses, it's even unclear that clipping actually results in a gradient field itself. Like I mean.
So clipping actually results in
a gradient field. So the clipped object, what you're getting, the vector, it's even unclear that corresponds to any gradient field.
I see. So you mean this result may not apply to high dimensional setting?
Yeah, I'm just saying that it not even may not optimize a single objective function even.
Yeah, thanks for the clarification. Yeah, that's interesting. Yeah, this is 1D. I don't have too much intuition about high dimension. Yeah, thanks. So so one thing you can do is maybe like typically the first thing in machine learning, you run your experiments on MNIST. So you might be curious about how sensitive are these kind of training algorithms to changing the clipping threshold, right? So you might have larger clipping threshold that doesn't clip up the gradient much, or you have much smaller clipping threshold that consistently clip a lot of the gradients. But some of the experiments we did, and I'm sure many of you have done, maybe showcase that sometimes actually this kind of performance actually is not so sensitive to the change of this kind of clipping threshold. So this got us interested in what exactly happened, right? Like, so maybe this kind of worst case instances don't exactly happen in some of these data sets. So one thing we did as to obtain intuition is to look at the angle of the stochastic gradients in the true gradient. So stochastic gradient just mean the gradient is evaluated on individual examples. So we are interested in plotting basically the angle between the individual gradient and stochastic gradients, the angle between those and the true gradient, which basically is obtained by taking the average. So interestingly, if you look at the cosine across all of these angles, you get these plots across different epochs. One thing that seemed to allude to, one interpretation we have by staring at these plots is that these cosine histograms seem to suggest some form of symmetricity, at least in terms of the histogram of the angles. So motivated by this, we basically want to think about, well, so if I look at the gradient geometry across different epochs, does this form of different forms of symmetricity maybe help to favor some kind of convergence that somehow can still guarantee that even though the gradient clipping operation is changing the gradient distribution quite a bit, but somehow it's still helping you minimizing the objective. So whether many of the real data set actually exhibit phenomena like symmetricity. So I will be a bit more formal about what that means in a bit. So if you open up some of the theoretical analysis of clip gradient descent, or for now, maybe take away the privacy noise from the equation for a second. So the privacy noise really just adding Gaussian noise on the clip gradients, average of clip gradients. And you can think about it still not changing in expectation, not changing direction of the clip gradients. So for now, let's think about a simpler case where just analyzing clip gradient descent where there's no Gaussian noise on top, right? But you can still think about the stochastic gradient noise because you are subsampling different individual examples to compute those gradients. And you can think about how those individual stochastic gradient noise will induce a distribution of clip gradients. Also think about what would happen if you just do gradient descent using this clip gradient estimate. Okay, so one thing you can prove that is kind of clean is that you can actually show that if you look at t iterations and look at the average of the following inner product, which is the inner product between the true gradient at every time step and the clip gradient you use every time step. So you take expectation of that. So this is the inner product between the true gradient and clip gradient. You can show that this object, this average inner product, is shrinking at the rate of roughly 1/√t. Right. So this is not exactly what you want, right? So typically, what you want is that, okay, you want to show that this inner product, right? If this inner product, the sum of these inner products, upper bound the sum of the true gradient norm squared. So if you somehow can establish this relationship and put this as the upper bound of the sum of the gradient norm squared, you can actually show that the true gradient is actually also vanishing. Right? The average gradient norm is also going down to 0 at basically the same rate. So from which then you can actually show that the algorithm will converge to a first order stationary point. So this is what we would like to have. So ideally, we would like to have that. And we know in the worst case that's not happen because there are some toy example we showed that basically this would not converge. So one thing we want to think about is whether symmetricity in the gradient distribution, in the GT in this case, actually help establish this blue relationship where the inner product is actually upper bounding the gradient norm squared. In other words, basically whether the individual noisy gradient is actually aligned with, noisy clip gradient actually is aligned with the true gradient. Okay. Feel free to stop me in case there are any questions. Okay, so I feel like my intuition oftentimes only holds in 1D. So let me give you a 1D example. So again, think about a loss objective, like the ones you've seen before in one dimension. You want to minimize some expected square loss, where the example is really drawn from some Gaussian distribution. Suppose you're running the algorithm and the SGD algorithm with clip gradient estimates stopped at the point of 0.5, right? So at the current point, your iterate is 0.5, and you can start evaluating the clip gradient distribution at 0.5. So here, remember the size just to denote the stochastic gradient noise. So there's true gradient plus noise. We cover individual examples to help you think about. Okay, so graphically, it just means that if I plot out the distribution of stochastic gradient, it roughly looks like this Gaussian distribution that's centered at 0.5 because the current iterate is 0.5. And I'm going to choose the clipping threshold to be 1, which correspond to these two red bars. All right. So what would happen when I apply this clipping threshold corresponding to these red bars on top of this Gaussian distribution that are in clip? Okay. So one thing we would like to leverage here is that this Gaussian distribution is symmetric around its mean. Right? So you can start dissecting this Gaussian distribution across different regions. Right? The first thing you might notice is that, right, there's something what we call the canceling region, which correspond to this light blue curve, light blue bar. I apologize if any of you is colorblind, so I will use this arrow to denote this region. So I'm going to call this outer two regions as a cancel region. The reason I'm calling this canceling region is that if I look at the gradients on these two intervals, right? If I take point-wise summation, I actually, if I take point-wise every point in this interval, I know that every single point would be clipped to this red bar, +1 and -1. Okay, and because they have exactly the same probability mass, I know that if I take average across these two regions with the clipping operations, I will exactly cancel these two regions out because both regions will be clipped down to -1 and 1, and they have the same probability mass. It will exactly add up to 0. Okay, so these outer regions will exactly get canceled out. Right? So when you take the expectation of the clip gradient, you don't actually need to think about this canceling region outside. Okay, so that's nice. Right. And one more thing you can do is that you can look at the region that's very much inside the neighborhood of the mean. Right. So this is within the clipping threshold. So all the areas here are not clipped and they're symmetric around its mean. So when you take average inside this green region with the arrow indicating, you actually recover exactly the true gradient. That's the purple line. So here you actually exactly align with the true gradient. And finally, you're left out with the region that's between the blue and the green curve, green bars. You don't exactly get this kind of nice cancellations in this case. But if you take average, you can see that because the probability mass are the same, but this region to the right is actually taking on a larger value because it's bigger than the clip threshold. if you average out these two regions, you actually get something that's aligned with the true gradient, which is taken on a positive value of 0.5. Okay, so the short takeaway from all this exercise is that if you think about the geometric structure or the symmetric structure of the gradient distribution and apply clipping on every single point, the average of the clipping gradient actually will be aligned with the true gradient. Okay. So you can start actually proving the kind of relationship where you take product between the true gradient and the clip gradient. It will be roughly in the same order of the norm of the gradient, the true gradient, or the norm of the gradient square. All right. So this kind of intuition can carry over to higher dimension, but the proof gets more complicated. So basically, you may not have the exact cancellation across different regions when you take it to higher dimension. But you can do similar kind of analysis to analyze this kind of expected clip gradient. So taking all these pieces together, basically you can show that for this kind of clip gradient descent algorithm, whenever the gradient distribution is actually symmetric, so if the gradient distribution happen to be symmetric, you can actually establish a relationship between the inner product between the true gradient and the individual clip gradient, and the true gradient norm evaluated on X. So true gradient norm of F evaluated on X. So here I'm simplifying using the H function to basically denote some monotone function of the gradient norm, which is interpolation between quadratic and the linear form. But to recap, this objective, this left-hand side is what the clip gradient descent algorithm is minimizing overall. And when the gradient distributions are actually symmetric, it will also minimize this right-hand side, which corresponds to the gradient norm, something proportional to the gradient norm. Let me pause here in case there are questions. Good. So obviously, if you assume the gradient distribution are exactly symmetric, that would be a very stringent assumption. So you can actually bring in the approximation. So basically, you can show that for every distribution you have, for every gradient distribution you have, and you take a look at the inner product between true gradient and clip gradient, you can approximate it with a nearby distribution that looks nearly symmetric. And you can decouple with this inner product on the symmetric distribution and what we call a clipping bias term, which can be rewritten as some kind of Rosenstein distance with some metric function. Okay, so basically, the closer you're to a nearby symmetric distribution, the better approximation you get in terms of the gradient. The true gradient and the clip gradient. Right. So you can now bring back the privacy noise, basically the Gaussian noise added to every round, and you can actually establish some sort of convergence guarantee for this kind of differentially private clip gradient descent, where the weighted average gradient norm is shrinking at some rates. That depends on how much the distribution of gradient in each round differ from a nearby symmetric distribution. Right? So for some of you, you might be familiar with some of these terms in the gradient descent analysis. Basically, the first term is something you get in terms of the gradient norm without clipping. So if you directly assume that you know the Lipschitz constant of the loss function and you never clip any gradients, this is sort of the convergence rate you get, where I'm hiding the Lipschitz constant dependence. But with the clipping, you can actually characterize how much clipping bias you have incurred during the trajectory by looking at the Wasserstein distances between the gradient distribution at every round and the nearby distributions. And the hope is that if this term is small, if the clipping bias or the Wasserstein distances to symmetric distributions are small, then your clipping bias is small, and the algorithm should still converge to a stationary point or a local minimum. All right. So this part is something that it's hard to establish theoretically. The gradient descent can be a complicated dynamics, but you can actually definitely evaluate it on a real data set, right? So one thing we did is to try to visualize the gradient distributions across different epochs, right? And we are running this kind of differentially private clip gradient descent. But note that the gradient distribution is living in a high dimension, so I cannot visualize it even if you show me. In particular, the way we would try to visualize it is to perform some kind of random projection down to 2 dimensions. So we try to do that across different epochs. If you look at the leftmost column, this is sort of the 2D projection of the gradient distribution. I will argue that it doesn't look very symmetric, and you can see them as the mixture of different clouds. But as you move on towards later epochs, the 2D projections start demonstrate some kind of symmetric behavior. So you can see across these 3 epochs, 5, 10, and 59.
So this is on a random, projected onto a random subspace?
Yeah, this is a random subspace, yeah.
And what happens if you project onto, I don't know, the top singular values or something like that?
Oh, we did not do that. That's very interesting. Yeah, we should have done that. We didn't do that. Yeah, my hypothesis is that it might preserve some of the property because of the plot I will show later in the second part. Because my claim is that most of the actions are contained in the top eigen subspaces. But one issue is that you might think that you might get very lucky with one random projection. So some of the behavior preserved if you start trying different kind of random projections. At least visually, it seems to suggest that this kind of symmetric behavior in the gradient distributions is happening at least after you take the random projections. Okay. So we have slightly more general results. I won't go into details. So for example, the kind of result holds with positive scale distributions in the sense that you may not be exactly symmetric, but on the non-symmetric part, you tend to be favoring in the direction of true gradient. It also holds for a certain mixture of symmetric distributions. One thing that I find to be kind of interesting that I won't talk in details is maybe the kind of gradient distributions don't exhibit the desirable structure to favor convergence. You might think about whether there's way to perform some kind of bias correction. One funny observation we have is that if you add noise before you take the gradient clipping, so before you take a gradient clipping, you add Gaussian noise to individual gradients. So that itself, we don't think will increase privacy, at least though we don't know how to prove it. But somehow if you perform this kind of pre-clipping noise, you can actually have you can incur an interesting trade-off between bias and variance. So by adding the pre-clipping noise, you will increase the variance in the gradient estimate, but you will actually you will bring the gradient distribution towards something more like a symmetric distribution. So you can reduce the bias, the clipping bias. So from that kind of trade-off, you can start proving some sort of gradient bias correction. You will have less than optimal convergence rate, but at least you can reduce the bias part that doesn't decrease with N or T. So any question about this part so far?
Stephen?
Yes.
Yeah, I'm wondering if something like data augmentation could have this effect of the fact that you suggest the pre-clipping noise could have.
Data augmentation, meaning if I add more data points? Or?
So, in data augmentation, for example, when you train image models, is sometimes every time you see an image, you apply some random perturbation to it, like random cropping or random flipping.
I see. So you think that might induce some interesting behavior in the gradient that might have this kind of pre-clipping noise phenomenon.
Yeah, I'm wondering if, I don't know, this is like your intuition.
That would be very interesting. I don't have intuition. Yeah, but it could be a thing to investigate for sure. Yeah, that's very cool. Thanks. Okay, so I have roughly 20 minutes. So let me talk a little bit about the second part. So this part is really thinking about clipping. But as I mentioned, clipping is really a form of doing projections for those gradients. And more broadly, I think we should really think about potentially you can benefit, the algorithm might benefit if you do projection of these gradients onto different kind of subsets that can leverage this kind of special structure of the gradients. I want to briefly talk about a result that explicitly think about how to leverage the low dimensional structure of the gradients, potentially improve the accuracy of DP-SGD. So this is work we did earlier last year, and by now there has been quite a few papers, especially some of the folks at Google have been leveraging this idea. So I hope that this can open up some more conversation. So we're definitely not the only one doing that, right? So, but to recap, the kind of convergence guarantee genetically for non-convex optimization, the kind of bounding can prove roughly looks like this, right? So you can capture the clipping bias by thinking about this kind of coupling with symmetric distributions. And then the remainder term is really the kind of DP-SGD without clipping. This is kind of the boundary you have if you don't do clipping. But importantly, if you look at some of the dependence, is that it actually scales square rootly in the dimension D. Right? So for some problems, you can actually prove that, like someone like Thomas will be able to prove that for some problems, this kind of square root D dependence is unavoidable. And intuitively, it's actually maybe in hindsight kind of obvious because the DP-SGD algorithm, even without clipping, right, you're adding D-dimensional Gaussian noise on the entire gradient estimate. So you're already adding D-dimensional Gaussian noise every round. And it's maybe not surprising that the convergence rate actually depends on square root D. But oftentimes, when you train really large model, you start to worry that this kind of square root D dependence or this heavy dependence on the dimension might be troublesome, especially when you're thinking about training millions of parameters or more than that, right? So one experiments we did is to think about what is exactly the effective dimension of the gradient distributions. Okay, so to more precisely, I mean the following. So there are different ways to look at this, but one way we can look at this is that at every single epoch, I can look at the gradient distribution across the examples. I can take the second moment matrix, meaning I take average across the individual gradient times its transpose. I can start investigating the subspaces of these gradients. One thing you can do is to basically look at the top eigen subspaces that correspond to the top eigenvalues. Right? So here's what we do for one of the experiments. So I think there are more details in the paper. I believe the ambient dimension, the number of parameters in this case is well over 130,000. But if you stare at the gradient distribution at different epoch, no matter you add noise or not, so this holds for SGD with and without differential privacy noise, you can see that actually most of the gradients actually live in a much lower dimensional subspace. In particular, you can tell that the eigenvalue has extremely fast decay, basically down to something around 50 in later epochs. Almost all of the eigenvalues will very quickly go down to 0. So that it's a phenomenon to hold without noise, without privacy noise, or with different noise rate within DP-SGD. Okay, so this gets a little interesting because if you tell me that most of gradients are actually living in a 50-dimensional subspace, like if you take the top 50-dimensional subspace, you can actually capture all of the behavior of the current gradients. But at the same time, the standard DP-SGD still add noise, the full-blown dimension. For example, in this case, well over 130,000. It felt like a waste, right? So there should be something that you should be able to take advantage of. So we start thinking about this algorithm. I think there's still lots of flexibility and variability you can think about in this space. But one thing we would like to take advantage is that potentially you can try to identify some of the gradient subspace using auxiliary public data. So maybe there's some side of public data that is drawn from similar distribution as the training data that can help you identify the subspace. But importantly, because the public data is so small, you may not be able to train a useful model just using the public data. Okay, so one idea, extremely simple idea, is to basically do the usual DP-SGD, but instead of doing the standard update, taking the dimensional gradient descent, I'm going to perform a orthogonal projection onto the top K eigen subspace using the public data. So identify using the public data. Okay? So you can basically perform this kind of low dimensional projection onto this gradient subspace. So you can start proving theorems about this. I personally think the theorems is not as interesting as whether this idea is just work in practice. So I'm just gonna skip the theory, but basically, if you think about both theoretically and empirically, this algorithm doing the projection onto lower dimensional subspace is really balancing between two sources of error. One error is basically due to projection because you're doing orthogonal projection onto a lower dimensional subspace, and the public data may or may not be representative for those gradient estimates. You can prove some uniform convergence guarantee, meaning if you draw sufficient number of public data, you might have low error, but you have error from this kind of reconstruction or projection. But you might potentially gain by effectively only doing the gradient perturbation is much lower subspace, right? So the typical bound of root d over n epsilon may be able to be improved to something more like root k over n epsilon if you only doing gradient update within those top K subspaces. Okay, so thinking about the two sources of error, you can start reasoning about when this kind of projection method would tend to do better. So it tend to do better when there's you need to add lots of noise in the gradient perturbation, and reduce it down from root d to root k can get you a big win. So that usually corresponds to regimes in which the values of epsilon tend to be lower, where you had to add more noise because you're at higher privacy regimes. So these are some of the results we ran. So yeah, I'm sure you can run it with better GPUs and with larger and fancier models, but this is sort of the result you expect. So as you decrease the value of epsilon, you tend to increase the level of noise. The technique that doing this kind of projection onto this gradient subspace, this is highlighted as DP-SGD, the projected DP-SGD, tend to do better across this data set. One interesting thing, basically we got a review that asks us to basically do that, is that what happens if you just do random projection? So you don't do any kind of public subspace identification, you just do something kind of like a Johnson-Minderstra's projection. So in general, it tend to do quite poorly, for example, in the MS regime. But somehow in fashion, MS is actually start getting some traction. Right? So this random projection, it still hurts the performance in terms of comparing with the baseline technique DP-SGD. But I would say it's quite interesting and already it's gaining some traction in terms of accuracy. So I think there might be some interesting questions there to build on top of this kind of random projections.
Yeah. Question.
Yes.
So for small values of epsilon, you're not getting any, you're getting more improvement, but for larger values, you're not getting improvement, you're going worse. Do you have any intuition for why there's this sort of crossover?
Yeah, so my intuition is sort of trying to be captured by this slide. So feel free to offer your intuition. But basically, when you have small epsilon, you have just like bigger win because you have larger amount of noise added. So the dimension reduction will actually be more effective in terms of noise reduction. So the noise reduction you get from this part tend to overwhelm the first part where the projection error. Yeah.
Hey, Stephen, can you, looking at the slide?
Which one? This one? Yeah, this one. Yeah,
the picture one. Yeah.
Yes.
If you switch, if you switch from, for lower epsilon, you do something, and you just switch to something else for the higher epsilon. Do you actually beat any of the existing trade-offs for MNIST or fashion MNIST or any of the datasets what you have looked at, like utility privacy trade-offs?
We do not know, but that's an interesting question. But in principle, so this one for MNIST, for example, I think you guys have error 95 for epsilon equals 3. 98 for how much epsilon? I don't remember.
3 or 4, I think. Shuang can confirm. I don't know.
Yeah, so that's impressive. But yeah, in principle, you from what you said, you just interpolate this red and blue curve. We didn't use CNN for this plot. I remember we actually used a fully connected one. Then for fashion analysts, we may have used CNN. So in particular, maybe by incorporating with the same architecture, we might be able to get closer to what you get for larger value epsilon. Yeah, that's an interesting question. Yes.
Did you? I may have missed this part, but when you were showing the plots about the frequency of eigenvalues, or rather the size of eigenvalues, was that for are we here in a least squares problem again? Are we back to sort of or are these the layers of a neural network? What is the model here?
This is neural network. I think we have both the MNIST. This is like a large-ish fully connected network.
Okay, yeah. So here we're just taking kind of the whole parameter set as a vector and looking at that as a single element of sort of Rn, and this is the eigenvalue decomposition of that. Is that right?
Yeah. So you're doing the gradient. So this x-axis might be misleading. The x-axis go all the way out of the screen because
yeah. And then the public data that you estimate the spectrum from.
Yeah.
This is now, because it's not, if this was like least squares, I would just do public data just means, the second moment matrix of the inputs. Here you are doing estimation of gradient eigenvalues. So does this mean you're training on public data? Sort of what are the gradients at for collecting the statistic?
So let me try to clarify. Maybe I missed one of the point you raised. We're not doing least square. We're doing image classification. So I think we do cross entropy. So we're not training on the public data. And implicit, maybe it's useful to talk about ones like.
Well, what I mean is that the public data is used to collect statistics of gradients.
Yes.
Is that gradients at optimum? Is that gradients sort of at initialization? The gradients are point dependent, especially when you're not in least squares.
So with the gradient at each iteration. Yeah. So at each iteration, I'm going to use the public data to estimate the top.
I see. Yeah. I see. So at each iteration, we stop and actually go and estimate the current spectrum.
Yes.
Got it. Okay, thank you. That was clarifying because using statistics from optimum when you're at the beginning of training. Or
that'd be funny. That'd be really weird.
That's what I thought. That's what I thought was being done. Although it could also, there could be a point where something like the optimum point is a proxy for other.
You might start. You have a better initialization potentially. So one thing. Sorry, say that again.
I just said thanks for clarifying that.
Oh yeah. So one thing I want to remark is that for this kind of method to make sense, or for this kind of public/private data to make sense, I think it's important to make sure that you're not using a ton of public data, because if you have that, you should just train your model on the public. If you're like 10,000 public data, you should just go use the public data. So we really want to make sure that in the experiments, the amount of public data we use are moderate, and we sort of not enough to train an accurate model. So what's interesting is that as you increase the public data to do the subspace estimation, you do get better accuracy, but it's tend to saturate pretty quickly. So that might be one nice thing about some of these models. You don't really need a lot of public data to estimate a subspace. And the dimensional subspace also have similar saturation phenomena. Like as you choose to estimate larger and larger, higher and higher dimensional subspace, you do get the improvement in the accuracy, but you also quite quickly saturate, right? So if you only choose to use the top 10 dimensional gradient subspace to train your model, arguably the performance is still quite bad. But very quickly, when you increase it from 20, 30 to 50, you actually, the benefit for taking high dimension to tend to saturate. Yeah. One more thing I want to show potentially related to computation is that maybe you don't want to actually compute this kind of substrate at every iteration. Is to be honest, is still a very expensive operation. So one thing you might hope for is that this gradient subspace does not change too much round by round. So you may be having some kind of scheduling on how to update the gradient subspaces. So maybe you only do it every 10 rounds in 20 rounds. And the nice thing is that you actually can skip many of the calculations when you do it every 10 rounds, you do the gradients estimation. Okay. So that would be sort of what I would argue for in terms of like practical usage of these kind of ideas. Okay, so I think I'm about to run out of time. Let me just quickly wrap up. So I also want to give a shout out to many of the recent work and a lot of them done at Google for basically taking some of these lower dimensional projection idea to other regimes and thinking about DP optimization. So there some recent work that think about unconstrained convex optimization and generalized linear problems. There's another work not done at Google, but similar to ours, that instead of thinking about just projecting, they're also thinking about perturbing the residual. One thing I noticed is that their work, they do rely on fresh public data at each step, at least inside the analysis of the algorithm, which I think may actually end up asking for a lot of public data for the training. And there's another direction people have thought about. There's a paper done with jointly with folks at Microsoft and maybe UW, and thinking about this kind of random projection idea, maybe not primarily for boosting accuracy, but for reducing the runtime and thinking about this kind of private SGD algorithms. Okay. So, and in summary, maybe some of the takeaway is that one thing we have been exploiting and leveraging and thinking about is whether you can start digging into this kind of gradient geometric structure and start leveraging this kind of structure to come up with different kind of algorithms. So for example, you might gain some understanding of what sort of structure that favor convergence when you have to do some kind of gradient clipping. And there's some ongoing work we are doing, trying to carry some of this intuition to federated learning, where maybe you don't actually clip the individual gradients, but you're asking the client to clip the individual model update that you're about to transmit to the central server. So some of this clip and bias analysis carry over. And in general, I think there's lots of interesting structure in the gradients that look like low rank or sparse that might favor accuracy. So I think there's lots of interesting questions, both theoretically and empirically, in leveraging this kind of structure to design some more accurate and more useful algorithms. So let me stop here, and I really would love to have more questions and discussion with you. Thanks.